Okay, so today we're going to talk about equilibrium. Um, this is pretty much the same thing as what we've been talking about before. We're just going to focus more on balancing forces instead of just the frictional force. So I want to do two examples today, example 11 and example 13 out of your book. In example 11, you've got a person who has their foot attached to a series of pulleys that are attached to a weight, and the idea is to stabilize the foot while at the same time pulling on the foot with a certain amount of force as part of a rehabilitation process. So if we look at what's going on with the pulleys, we'll be able to figure out how much force this whole system is pulling on the foot with. So the main pulley that the person's foot is attached to is here, and a cord or pulley cord is coming off of that pulley like this. That comes down to another pulley where the mass is attached, which is applying this force of tension. They tell us a couple bits of information about this system. The angle between the horizontal and the cord is 35 degrees in both cases. This is going to help us figure out the amount of force and the direction of the forces that are acting on the foot. Okay, so let's look at the system. If all of the forces are acting from this point, then the force of the rope going up like this is acting in that direction, and the force of the other rope is acting down in this direction. Here's the horizontal here, and we can split that force into the horizontal force and the vertical component. The reason the person's foot doesn't go up and down, if these angles are the same, then the vertical component of those forces will cancel each other out. In the first force here, the vertical component is upward, and the second force, the vertical component is downward. The force of tension in those ropes is, we're going to find out in a second, is exactly the same, so those are going to cancel out. The horizontal pulling force is just going to be that force of tension in the x direction for both the ropes. Okay, so let's look how to solve this problem. For the y direction, we can again use Newton's laws and say that we definitely don't want the injured foot moving up and down. And they tell us in the problem that the foot is stabilized by this setup. So we would expect that the acceleration of the foot in the y direction would be 0, or that the net force in the y direction should be 0. If we look at our diagram up here, we can tell that the y component of the two forces is equal to the sine of theta times the force. Just a little bit of trig, so I can rewrite that, and I can say that force 1 times the sine of theta minus force 2 times the sine of theta should be equal to 0 newtons. I've used the minus sign here because force 2 is pointed downward. If I look at this, I can factor out the sine of theta, and that's 35, it's non-zero. So I know that the force 1 minus force 2 has to be equal to 0 newtons. This is what needs to be making this whole term equal to 0. And if I solve that, I'll find that the magnitude of force 1 is equal to the magnitude of force 2. So all we've done is prove that the tension in this cord is the same in both places. So the next thing that I need to do is switch over to the x dimension, and I'm going to say that the net force in the x dimension is going to be equal to the mass times the acceleration in the x dimension. Again, we don't want the foot actually moving or accelerating away from the person. And again, they told us in the problem that the foot was stabilized, so it was at rest, at equilibrium, so there should not be any acceleration. We said earlier that the net force here is going to be the force from the first rope times cosine theta for the x component, and the x component of 2 is going to be, again, cosine theta, minus the force that the foot is pulling back with. This whole apparatus is pulling to the right. The foot is going to resist that pull and pull to the left, and that's what's stretching the foot out and causing the system that we want so that the foot is rehabilitated. This whole thing needs to be equal to 0 newtons. Again, we know that force 1 and force 2 are equivalent to each other. We just proved that a second ago. So I can rewrite this as just 2 times the force times cosine theta minus F is equal to 0 newtons. So the force exerted on the foot is equal to 2 times the force from, let me put force applied here so it's less confusing. It's equal to 2 times the force from the pulley times cosine theta. If I plug in the known values, here if we look at our free body diagram, the thing pulling on the rope is the block. So it's the force of gravity. So we know that this force that's coming from the string is actually just the weight of the block. So this is 2 times mass times gravity times cosine theta. And if I plug all of that in, I'll get that the foot is being pulled on with a force of 35 newtons. The next problem that I'd like to look at is example 13. And in this situation, you've got an airplane. Let's see. And this airplane's moving through the air, and we're trying to figure out the force of air resistance and the lift produced by the plane. We're told that the plane's engine is producing a certain amount of thrust, which I'm going to call capital T. The plane has a certain amount of weight that is directly downward, which I'll call capital M. There's a force of air resistance, which is resisting the motion of the plane, which I'll call capital R. And there's lift, which I'll call capital L. And the lift is coming from the wings, and that's what's keeping the plane in the air. So the plane is actually flying at an upward angle of 30 degrees. We can actually solve this problem really similar to an incline problem that we did before by realizing that if we just rotate the coordinate system to be along the axis that the plane is flying on, it'll simplify the problem quite a bit. That means that our force of air resistance, our thrust, and our lift will all be in one dimension. The only thing that's not in one dimension is the weight of the plane. If you remember from a few days ago, the x component of the weight when we've rotated the coordinate system like this is actually equal to the weight times sine theta, and I'm using a negative sign here to show that it's actually in the negative direction in the coordinate system. And The y component, again, is downward, so negative, and it's cosine theta. This gets a little confusing, remember, because in projectile motion or decomposing vectors normally, usually cosine is related to x and sine is related to y. When we rotate a coordinate system like we did here, that's when things get flipped like this. So you may want to take a little extra time to make sure you've got that clear in your head. Again, we're going to solve this problem by using Newton's law. We're going to say the net force in the x direction is equal to mass times acceleration in the x direction. If the plane's in equilibrium and it's flying at a constant velocity like they said, there's no acceleration, so this whole thing should be equal to 0. The forces acting in the x direction are the thrust minus the air resistance minus the x component of the weight of the plane. And that should all be equal to 0 newtons. I can solve for the air resistance, which was one of the things they asked me to solve for. And the thrust and the weight were things they gave to us. The weight was equal to 86,500 newtons, and the thrust was equal to 103,000 newtons. So I can plug in those values and find the air resistance. I can also find the lift by going into the y dimension and doing the same thing. So the net force in the y dimension is equal to mass times the acceleration in the y dimension. Again, it's in equilibrium, it's not accelerating, so this should be equal to 0. The forces acting in the y direction are the lift minus the y component of the weight, and that should be equal to 0 newtons, which means the lift is actually equal and counteracting the weight of the plane, which makes sense. And again, we can plug in the known values to find that. Right, your homework tonight is actually going to be problems 52, 53, and 59. If you have any questions, I'll be there after school today, so just stop by in the lower school science lab.